Well, good evening, everyone. Welcome to the Monday Night Bible Study. Tonight we're doing something a little different. As you can tell, it's not Aaron or Max. Usually, you guys are left with or stuck with them. I say stuck with them. They do a great job, but now you're stuck with me. You're stuck with me and DJ, and I'm really excited about tonight's study because it's something that we haven't quite done on a Monday night study before. We haven't done this topic before. And so I'm super excited about it. And I hope you're excited about it as well. DJ, he's going to be leading this study for us. So DJ, why don't you go ahead and tell us what we're going to be talking about this evening?
Yeah, yeah, thanks, Ruben. And definitely, can't hold up to Aaron or Max. So it will be different, and hopefully it will be special as well. Like you said, it's a little bit different topic tonight, and it's a topic that I've been fairly passionate about for a little over a decade now. So I'm a chemical engineer by background, and about 15 years ago, I kind of started getting in my head that I wanted to go to graduate school, and I worked pretty hard, got to the top of my class as an undergrad in chemical engineering, got into a PhD program, and for various reasons started doing research in biomolecular engineering, got accepted into a PhD program at Yale University in Connecticut, and I did research up there for about a year and a half and got my master's degree. And a lot of the topics that I did research on were topics that around the same time in 2009, Stephen Meyer, who come to admire quite a bit, wrote this book, Signature in the Cell. It's a pretty lengthy book. It's about 500 pages long. And it's really strengthened my faith a lot over the last 10 to 15 years. Everybody kind of has their own thing that they kind of lean on if they're having questions or doubts. For some people it's prophecy, for some people it's maybe evidences in the flood, for other people it's the textual consistency of the Bible, how we have so many different manuscripts and things. For me, those things all build my faith, but really one of the things that's most central to me is the content of this book. And I've just seen so many of my friends and people that I know over the last 10 or 15 years that I've watched just kind of fall away, and you hear people say that they're having questions or doubts. And this is something that I've thought time and again. I wish more people knew and understood some of the evidence that's presented in this book. So I just wanted to try to help pass along some of that information that, has really been pivotal to my faith over the last decade or so, as I said.
Okay. Well, you mentioned how you went through this graduate program, started having questions, started looking into those sorts of things. And I know that there are people who say, well, you shouldn't have questions, because these questions are just going to lead to doubts. These questions are just going to sort of lead you away from God. If you look into this, then you're going to lose your faith. What would you say to people who have that sort of mentality?
Well, I mean, I think the scriptures are pretty clear. I mean, if you're, obviously we should have a Bible-based faith, but the scriptures don't only point to themselves. Romans chapter 1 and verse 20, I think makes a pretty clear point that, that we should not fear the evidence in the natural world. And I don't know if you have that slide up there. Yep. So Romans chapter 1 and verse 20 says, God's invisible qualities, his eternal power and divine nature have been clearly seen, being understood from what has been made, so that people are without excuse. So I think I think it's critical to us to not only have to not only have faith that's based on evidence in the scripture, but sometimes we'll meet people who don't believe the Bible. So we need to have arguments for God, for the existence of God, that are based in the natural world as well. And I think that in and of itself is scriptural. So kind of in this study, we're looking at the natural world, at things that have been made. That's obviously a direct reference to nature. And we can't directly see God, but we can indirectly see him, manifested in his creation. And I think one of the interesting things specifically about when you start talking about biomolecules, about DNA and protein, they're literally invisible to the naked eye. They're so small you can't even see them with a microscope. Has to do with the wavelength of light and the way that it refracts off of things. That these molecules are so small that they're literally invisible. You can't get a microscope powerful enough to see them. Yet once you look into what they're doing, it makes pretty clear that that there's some intelligence that went into this, a pretty vast amount of intelligence that we can't even comprehend. And I think it's to the point that it makes people without excuse to disbelieve. So, so I think moving along with that, I think there's some people who are watching this, just kind of starting out, that they may think, well, I don't specifically have any doubts about the existence of God. That's not something that I struggle with. And if that's where you're at, I would just say that one thing to consider is pretty much someone is pretty much guaranteed to have doubts or questions, someone you love. And if we don't teach them then what the world is going to teach them is, is pretty much a very anti-God message. That's the world that we live in today. Richard Dawkins is probably one of the most outspoken and famous for this. He's written quite a few books. And one of the quotes from one of those books that I'd like to read for you, it's religious fanatics want people to switch off their own minds, ignore the evidence, and blindly follow a holy book based upon private revelation. So we can clearly see that Richard Dawkins, he's a very smart man. He's done a lot of interesting thinking, a lot of interesting work, but he clearly has very little respect for anyone who has a religious background. You can see there his view on faith and religious people is that they just blindly follow. And essentially what he wants to teach our children is if children understand that beliefs should be substantiated with evidence as opposed to tradition, authority, revelation, or faith, they will automatically work out for themselves that they are atheists. I mean, so that, as a Christian, something like that, if you're not used to reading statements like that, or you don't watch interviews with people like this on a frequent basis, that kind of makes your blood pressure go up a little and can kind of make you frustrated to see this because you know that your faith is based on evidence. So I think it's important that we look into these things and talk about these things, because if we don't talk about it and we just assume that our kids will develop the same faith that we have and have the same appreciation for the existence of God that we have, that's going to be lost on the next generation and lost on young people and perhaps old people as well who are struggling with doubt. So I don't know, Ruben, do you have any other thoughts on, people with maybe a completely different worldview than us and, maybe kind of the why we should be even looking at this in the first place?
Yeah, one of the things I would say is, I have friends who, like, this stuff matters zero to them. Like you said, they believe based off of something else completely. And so for them, this is not interesting. But if you're one of those people and you're listening, it's exactly as DJ said. If this doesn't work for you, if you don't have doubts and questions, if you believe and hey, you're a believer and no one's going to change your mind, more power to you. But maybe your kids or someone or your niece or your nephew, they are going to maybe they will struggle with this, and having this knowledge on hand will help them or help a friend or something along those lines. So yeah, absolutely. This is extremely important. And so I believe your next section, you're going to talk a little bit about potential causes. That's the next slide that I have up for you. And so why don't you talk about potential causes that, any effect, are essentially by these potential causes. Why don't you go ahead and take that away?
Yeah, thanks, Ruben. So essentially what we're going to do is go through the same basic arguments that Stephen Meyer looks at in his book. And I think he makes a really compelling case for, what in the scientific community is called intelligent design. And the way that we like to present this is essentially the same way he presents it in the book. And that is that for any cause, for any effect that you observe in the natural world, you pretty much can boil down all of the causes to one of three potential causes. That's essentially chance, necessity, or intelligence. So those three causes explain pretty much every effect that you can observe in the natural world. And I would challenge you to come up with a cause that isn't one of those three or a combination of those three. So, to kind of break this down a little bit more, and we're going to, eventually get into the biochemistry of it. But, just think about it with a coin toss example, I think is one, way to put it. But basically, if you have just a quarter and you're going to flip a quarter, lands on heads, you would say, okay, it landed on heads by chance. But then if you start flipping that quarter repeatedly and maybe 10 tosses in a row, it lands on heads, you would start to question, was that really by chance because it was an improbable event? So you may start examining the quarter some and say, well, actually, this is a weighted coin, or maybe it has, both sides are heads. There is no tails. So it's by necessity that it was going to land on heads, either by the fact that it's the only side, or by the fact that maybe the head side is weighted in such a way that, gravity forces it to land on heads every time. Now, let's say that you examine the coin and, it's equally weighted. There's heads on one side and tails on the other. And you flip that coin and 10 times in a row, it still lands on heads. And then maybe 20 times in a row, 30 times in a row, 40. Eventually, it would land on heads so many times that the person who's flipping it, you would start to question, are they messing with you? Are they doing some sort of sleight of hand or something like that? And that's where you would say, okay, that was an intelligent cause that made it look like it landed on heads every time, but that wasn't actually the case. And, you could come up with countless examples of things that you see in your everyday life that are always going to be explained by either chance, necessity, or intelligence, or some combination thereof. And it's that basic logical structure that Stephen Meyer approaches the problem of the origin of life. And that's kind of what we'll get into next. But and specifically that problem is referred to as abiogenesis, which is essentially life from non-life. So yeah, on that point, I don't know, Ruben, if you'd want to have anything else to add to the potential causes of different effects that we observe, but that's the basic structure of the argument and the basic way that we'll be looking at this.
No, that's good. And so why don't you go ahead and move into your next section here on the pillars that undergird a naturalistic worldview.
Yeah. So moving on, Ruben, we talked some about, if you're going to approach this, if you just woke up on an island one day and you had no memory of the Bible or of anything from your past, if you were going to try to explain how you got to where you are, how everything around you exists, and you were going to try to do it by purely naturalistic means, I would propose to you there's basically three basic pillars that you need to explain in order to do that. And the first is really the origin of matter. You need to explain, how did all this stuff around us get here in the first place? And over the last 100 years or so, I think most scientists would agree that they think that they've made great strides in coming up with an explanation of how the universe came to be and how it exists as it is today. And, the Big Bang Theory, everyone's familiar with, even made a TV show about it. Before about 100 years ago, scientists in general, the consensus was that the universe was essentially infinite. Even philosophers going back 2,000 years thought the universe was infinite. And then really in the last 100 years, that's become, an old thought from a scientific standpoint. Everyone pretty much agrees there's a beginning now. And things we don't even have time to get into with quantum cosmology, essentially try to explain how matter came into existence in the first place. So that's, if you woke up on that island and you're trying to explain how you got here with a purely naturalistic explanation, you'd have to explain the origin of matter. Next, you'd have to explain how that matter became life. And life, from a scientific standpoint, is essentially self-replicating cells. If you get down to the simplest life form that we know it, you have to have a living cell, which, has a cell wall, has DNA inside of it. And that DNA is what has all the instructions that allow the cell to replicate and create new cells. So, obviously, if you see a rock or, an animal, even like a 3-year-old can tell you the rock is not alive and the animal is alive. Well, at the most fundamental level, what gives that animal life and the rock no life is its ability to grow and to heal itself. So if I damage that rock or, watch that rock over time, that rock's not getting bigger and it's not healing. It's dense, whereas the animal does. And at the cellular level, what enables life to do that is its ability to replicate, to take one cell and copy it into 2 cells or more. So what naturalists, if someone with a naturalistic worldview, what they need to explain is how that first living cell came into existence. And then from there, we're all familiar with, for the last 150 years or so, the concept of Darwinian evolution. This, idea obviously propagated by Charles Darwin. Darwinists would say that cellular life, once it was on the scene and in existence, the mechanism of Darwinian evolution can now explain how we get all complex life today. And they'll show you this picture of a tree and say that, well, all life came from this first self-replicating cell. That's the trunk or the roots of the tree. And then it expanded into all the complex life forms that we see today. Now, I would submit to you that this is essentially, the worldview of the naturalists. And it's these 3 fundamental pillars that undergird, I would say, the faith of someone with a naturalistic worldview. So I would also argue, of these 3 pillars, I think the center one, the origin of cellular life, the origin of the simplest life forms as we know it, is the one that the general public understands the least. My 3-year-old son, I can take him outside at night. He can look up at the stars and be amazed at the stars and see them and understand that they exist. I could take him to the zoo and he can be, amazed at the different forms of animals that are there. But the idea of cells and cellular life and them self-replicating, that's a kind of an abstract concept to a child and even to an adult if you haven't, been formally taught how that works and what that is. So not only would I say that center pillar, the origin of life, is the least known pillar in this worldview, I would say it's also the weakest pillar for reasons that we're going to be talking about this evening. So, and I think these are important reasons. If someone was to try to attack my faith as a Christian, the best way for them to do it is to go after what they view as the weakest pillar of my faith, and perhaps the one that maybe they think I know the least about. I think we see this a lot of times when people fall away. They'll, they get attacked in areas that maybe they don't have a lot of knowledge, and then they fall for deceptive lies or things that they don't fully understand or appreciate. So really what Stephen Meyer does in his book is he does not try to prove that the universe is a young universe. He does not try to disprove Darwinian evolution. He essentially shows how you can basically grant those premises to someone who has a naturalistic worldview and still prove to them, I think, beyond the shadow of a doubt, that the origin of the first cellular life could not have come on the scene without the agency of an intelligent being. And really does so by going through chance, necessity, and intelligence, and shows that chance and necessity and no combination thereof cut it whatsoever. So that's essentially what we'll be looking at. And Ruben, I don't know if you have any additional thoughts on that topic, or if I know you're with me so far. We've talked about this some in good detail, and I know you have a good background on this as well.
Well, I don't have your background, so I'm definitely going to let you take most of the stuff here. But one of the interesting things I've come across just in my conversations with people, because that's one of the things I would bring up to someone who's an atheist, and usually I end up talking with people who are very militant atheists. I know there are a lot of atheists who are very good people, but I tend to talk to ones who have just a axe to grind with regards to faith, and they don't like faith or God. But one of the things that will come up is I'll bring up this problem of the origin of first life, and they'll just say, well, evolution, Darwinism doesn't cover that. Darwinism begins after the first replicating cell. And it's like they don't realize the problem of, yes, Darwinism technically doesn't begin until evolution technically doesn't begin until after the origin of first life. But you see how that's a problem if we can't explain that, right? If we can't explain the origin of first life, then Darwinism, natural selection, none of that ever gets started. And so, yeah, it's absolutely important if we're going to have a naturalistic worldview, we have to be able to explain the origin of first life. And so I'm glad that you picked that up. And it's interesting, in your notes, I see you write, this is not a God of the gaps argument. And I believe Stephen Meyer's argument is not a God of the gaps. I believe it is positive evidence, a positive argument for an intelligent designer, much that we would see like in other sciences like archaeology and stuff. But it's interesting that it's almost like some atheists have a naturalism of the gaps. It's like, we don't know how it happened, but it has to be naturalistic. And it's just an interesting worldview that I've seen in discussing this with others.
Yeah, those are great thoughts, Ruben. I'm glad you brought up a few of those things. I actually want to add on to one point you were making. I think it's in Stephen Meyer's, in this book. It may have been in one of his other books. I've read a couple of his books, so I'm getting it mixed up. But what you're talking about a lot of atheists, I think a lot of people in general, don't understand the differentiation, like you're saying, between explaining the origin of the first life and explaining, evolution. Like, evolution cannot explain how the first self-replicating cell formed. And the reason being, we can just talk about it briefly, because I think it's important for laying the foundation of, what we're trying to disprove. But essentially, Darwinian evolution, it relies on a self-replicator in order to, progress change over time. The story that Meyer uses, he essentially says, imagine driving home, from church or from work or whatever, and you suddenly fall into a hole. How are you going to get out? And somebody presents this riddle to you, and you say, oh, I've got it. I know how I'm going to get out of that hole. I'm just going to go to my house, and I'm going to get an extension ladder out of my backyard. I'm going to bring it back and put it in the hole, and then I'm going to climb out the extension ladder. And, you're like, well, that's a great solution, but it does beg the question, how'd you get out to get the ladder? And it just creates this circular, this endless circular loop where you've explained a mechanism of how you can get out of the hole, but you didn't explain how you got the ladder there in the first place to get out. Right. And that's really the differentiation. You can't have any form of evolution working in any sort of mechanistic way without a self-replicator in the first place. So I'm glad you brought that up. That is kind of a key point, I think, when talking about this.
Yeah. Okay. So you talked about how if there is an effect, there must be, one of three causes. It's either has to be by necessity, has to be by chance, or it has to be by an intelligence. And one of the, I guess, ways that this could be explained, the first replicating life, is, well, it happened by chance. Just give it enough time, it happened by chance. So why don't you explain that? I'll turn it back over to you.
Yeah. So, and I'll explain the chance hypothesis a little bit, and I'll also say we're not going to talk much about the necessity hypothesis, but the simple reason, and Meyer disproves it in the book, is it was understood shortly after the structure of DNA was uncovered in 1953 that the necessity hypothesis, the idea that the chemicals in DNA somehow automatically created the sequence and created the information that's there that's so hard to prove in the first place. So essentially, the necessity hypothesis is really not something that really anyone leans on at all. So the chance hypothesis is really what most of your, like you said, militant atheists go to and cling to try to essentially prove that the origin of the first life could have happened in the first place without any need for an intelligent agency. So I would say also that the mindset of the chance hypothesis has really bled over into really the general public's mind. If you watch any sci-fi movies, or if you take a college class or read a college textbook, even just on the news, I've watched some news clips recently talking about asteroids flying by, and one recently with Neil deGrasse Tyson, a famous astrophysicist, and he was super excited in this news clip because he said, we know that these asteroids, that they can contain the building blocks of life, they can contain amino acids, and that means that it's just a matter of time before one of these goes by and crashes into a planet and it has the right building blocks there, and their life is spontaneously going to form. So I would say that the chance hypothesis, the idea that, okay, yeah, it's unlikely for life to form by chance, but the universe is such a big place and it's been here for such a long time that there's been so many opportunities for it to happen by chance that it's just inevitable that it would happen eventually. So I think that is a pretty widely taken and widely accepted view by most people who do not believe in God. They would generally say that, well, just because the universe has been here for so long, because it's so large and so vast, that it's just life is bound to happen eventually by chance. And I think the thing that most people don't understand, and I'll self-admit, I really did not fully appreciate until I read Signature in a Cell, the problem of really what Meyer calls combinatorial inflation. So we're going to talk a little bit about that, but that's really the problem with the chance hypothesis. Is it's a problem of combinatorial inflation. And if you have no idea what that means, it's okay. I'm going to give you an example to try to illustrate what combinatorial inflation is. But essentially, it's showing how the numbers get so large in terms of the number of possibilities that it just does not make sense that something could happen by chance. So essentially, I want you to imagine that you are in a stadium, whether it's a football stadium, basketball stadium. I want you to imagine that there's 10,000 seats in this stadium, and that you and I are going to go there together. You're going to go sit down, and we're going to play a little game where essentially I'm going to try to guess which seat that you're sitting in. So obviously, to know what my odds are, I need to know how many possible seats there are to choose from. So if there's 10,000 seats, I obviously have a 1 in 10,000 chance of guessing your seat correctly. So from Richard Dawkins' evolution, origin of the first life approach, he would essentially say, yes, this is what the creationists do. They say that, yeah, it's really slim odds of guessing which seat you're in, but the analogy would be that, yeah, the complexity that we see in life is great. The odds of it happening by chance are really slim, but the universe is a really big place. It has a lot of opportunities and a lot of time to try to make those chances actually come to fruition. So the interesting thing about this is if you were to take this little game, which would probably be much less interesting than actually watching the game, but if I were to take one guess every second and continue doing that continuously throughout the game, after 90 minutes of guessing, I've already guessed over half the seat numbers. I've already got 5,000 guesses in the bank. And over the course of a 3-hour game, I've guessed every possible seat. So there you can see, with enough time and chance, I've now guessed all 10,000 seats. You had to be in one of them. So you can see I've taken something that was a extremely improbable event, 1 in 10,000 odds on a single guess, and boom, I made it happen, in the amount of time that it takes to play a football game. So this is the type of logic that a lot of times you'll see coming back at you as a Christian or creationist, that, yeah, you people, creationists, you talk about the complexity of life, but what you don't appreciate is the universe has been here for so long and it's so large that you don't take into account the number of possibilities for that life to come into existence. Well, I want to do a second round of this little game and ratchet up the probabilities a little bit, because obviously the odds of the odds of the first life forming are a little different than guessing 1 in 10,000 seats. So this is kind of illustrating what I was talking about with the problem of combinatorial inflation. So now let's imagine the same stadium, there's the same 10,000 seats, but now instead of just guessing your seat, Ruben, I'm going to try to guess all 10,000 people in the stadium seat numbers. So let's say I have a list of names, 10,000 names long, and I know all the seats are numbered 1 to 10,000. So then the question becomes, well, if I want to know what my odds are of doing that, I need to know how many possibilities there are. And so you could ask yourself, how many people would I want helping me in order to have, a chance of being able to guess that correctly? And how much time would I want to be able to actually make that a, feasible proposition? So how much time would you want? How much help would you want? I don't think I would sign up for this game. It sounds pretty boring, but it's to illustrate a point. So, I think most people would not correct, unless you've taken a statistics class or, something about combinatorial mathematics, most people probably do not realize how many possible ways there are of seating 10,000 people in 10,000 different seats. And the numbers really blow up really fast. So essentially, it's not 10,000 times 10,000. That would still be a big number, but that's that math does not work out correctly. Essentially, what you have to do is it's called you have to find the number of total possible seating arrangements. It's called a factorial. So the number of possibilities is 10,000 factorial. That's the 10,000 with the exclamation point at the end. And what that number means is you take 10,000 and you multiply it by 9,999, and you multiply that times 9,998. And I won't go all the way down, but you keep going all the way down to 1. And if you think about it logically, it makes sense, because if once you guess the first person's seat number correctly, if Ruben, I was guessing your seat number, I had 1 in 10,000 odds on the first one. Now that you're seated, now there's 9,999 seats left. So let's say Max is there, and I'm going to guess his seat number. Oh, I got it right. I only had 1 in 9,999 chance of that. Now the next one is, now there's 2 seats taken, so now there's 9,998. So you can see going all the way down. So if you write this number as a normal number or exponential in scientific notation, it actually works out to about 10 to the power of 35,000. So that's a 1 with 35,000 zeros behind it. So it's an incredibly large number, incredibly small odds to actually guess that seat number correctly, right? The number blows up extremely quickly. Now, I think the thing that most people would be surprised to know is that this number is so large that, like, there's some problems that just cannot be solved by supercomputers, right? There's obviously infinity is a concept that we understand in principle, but numbers can get so big that they're not infinity, they're just extremely large numbers. But computers can't solve everything, supercomputers can't solve everything, and time and chance can't solve everything either. One of the points that Meyer makes in Signature in the Cell is he talks about the probabilistic resources of the universe. So in the little example that we just did, that problem exceeds the probabilistic resources available to really the entire world. So if you had 8 billion people and they're making guesses constantly for 10 billion years, and they make one guess every second, I think I did the math, that was like 10 to the 27th power, if I had that on the slide. So you can imagine you've only made 10 to the 27th power guesses, and you have 10 to the 35,000 power opportunities. So you're just not going to get that. The odds are not in your favor. So essentially, that's the point: is time and chance can't solve everything. And interestingly, the probabilistic resources of the entire universe are only about 10 to the 140th power. So just for the sake of time,
and could you explain?
I won't go into the details of how that number gets calculated, but 10 to the 100. Oh, yeah, probabilistic resources of the universe.
Yeah. Just explain, because I don't think we explained that probabilistic resources and what that is and how it relates to this problem.
Okay, yeah. So, the probabilistic resources in this problem are essentially, the number of people that you want to have working together to try to guess, how many what your possible seat arrangement is. And if every second each one of those people are making a guess, and how much time do they have to make that guess? So your probabilistic resources are essentially, what is your capacity for making guesses when you have a chance problem? So, in this example, if you've got every person on the planet guessing every second, even if they do so for 10 billion years, they're never going to get this problem right. They're never going to be able to guess the correct seating arrangement.
Right, because you only have the probabilistic resources to make 10 to the 27th power guesses, but there are 10 to the 35,000th power There are that many possibilities, and so it's essentially impossible to be able to solve this problem of guessing, where 10,000 people are seated in 10,000 seats in a stadium like that.
Yes, and so kind of hold this example in your mind, and something we'll get to is really talking about really the mathematical absurdity of this problem as it relates directly to the origin of the first cell. And essentially the probabilities work out similarly. Now, if you want to click forward one slide for me, Ruben. So, here's just a random sequence of letters. I think this was about 56 or 58 characters, something like that. So if you do the math on it, there's like 28 to the 56 possible combinations of characters here. So this is a highly improbable sequence of characters. As you can probably guess, I just randomly typed this in. There is no design or intent to this. If you put up the second sequence of characters, if I told you that I just randomly typed this one in, you probably would not believe me, and for good reason. In the beginning, God created the heavens and the earth. Now, these two sequences of characters are the same length, and they have the same number of potential characters in each position, but the first one conveys no specified information. It doesn't have any meaning other than just gibberish. The second sequence of characters, it's a sentence, it's English, it has meaning, it's in the Bible, it carries a lot of external information beyond just the sequence of characters itself. So that's what we call specified information. And I think I put on there too the probabilities. I think it was something like 1 in 10 to the 80th. So our minds are wired and designed 1 to the or 10 to the 79th power possibilities, essentially. So our minds are designed in such a way that we can just look at gibberish or look at specified information, and we automatically, if you think back to chance, necessity, intelligence, we automatically can make a good assessment about which one of these bits of information are there by chance, and which one of these pieces of information are there by design. And it's with this, and this so far we've been talking for over 30 minutes. We haven't really talked at all about DNA or proteins, and that was for a reason. I really want to lay a foundation and really get to this point of Shannon information versus specified information, because that is really the key point to understanding some of Meyer's central arguments in the signature in the cell. And I think really understanding and appreciating these points will help people better understand that when you sit in a biochemistry classroom or sitting in a biology classroom and you're a really smart professor at the front of the class, just scoffs and laughs at anyone who thinks this is designed, that being, cellular life, they're not going to talk about Shannon information versus specified information and talk about how it's incredible that even at the cellular level, we see a great deal of specified, highly improbable information. They're not going to talk about that, but that is very real evidence for the existence of a designer. And I think it's a key point to hone in on. And so anyway, I wanted to spend some time on this because I think we can lose people quickly if we just jump in and start talking about biochemistry, and if half the audience doesn't have a chemistry background. But I think most people can understand a 55 or 56 character long string of characters, right, and understand the difference between gibberish and a sentence that actually conveys information.
Yeah, with that first sentence there that's on the screen.
So
you could have.
Yeah, Ruben, I don't know if you have anything else you'd want to add on that point. Yeah.
Oh, sorry. You must have paused there. I didn't know. But with that first sentence there that you have on the screen, you could have dropped a basketball on your keyboard and that could have come out. But if you said, hey, I dropped a basketball, and that second sentence came out, in the beginning God created the heavens and the earth, I just dropped a basketball on my keyboard. Well, no one would believe that, right? Both of these, and I'm pointing, like everyone can see me pointing on my screen, but both of these sentences have the same improbability. They're both equally improbable, right? But one of them is Shannon information, and a Shannon information just means essentially it means there's nothing there. There's no meaning there. There's no design there. And the other is specified information, and that means there is some meaning to it. There is design. And the reason why we would say, well, this specified information, in the beginning, God created the heavens and the earth, that didn't arise just by chance, is because sentences with specified information are not that common. Gibberish, if I drop a basketball on a keyboard and this phrase popped up twice, well, that'd be very unlikely. But we would expect gibberish if I dropped a basketball on a keyboard, right? And so that's sort of, I don't know, the layman's easy explanation of Shannon information versus specified information.
Exactly, Ruben. Yeah, no, you nailed it, and good job making it a little more concise. And these, I think, whether you're talking about flowers in a field, whether you're talking about strings of characters, in a book, or whether you're talking about the seating arrangement of people in a stadium, these are all examples of combinatorial inflation. The number of possible ways of arranging those things, the number of possible combinations, as it grows, they blow up, exponentially, more than exponentially. And what I think Richard Dawkins, and he talked about militant atheists, what a lot of them, I think, try to intellectually dupe those who would believe in a creator. The way that they try to intellectually dupe us is they'll write these long books with, lots of meandering explanations about how essentially, well, you do see these highly improbable things happening all the time in nature. And the fact that we exist, the fact that we're here, yeah, it's highly improbable that it happened by chance, but it happened. So it had to have happened by chance. And that completely, ignores the point about the distinction between Shannon information and specified information. Like you said, you drop a basketball on a keyboard and it spells a sentence or writes a book or, writes one of the works of Shakespeare. You shouldn't sit back and say, well, it happened. So it must, even though it was improbable, it must have happened by chance. No, there's something else going on there. Someone did that with intelligence. Someone did that by design. And, that's our uniform human experience. So we should take our uniform human experience and apply it to what we see when we're trying to look for how did the first living cell come into existence.
Absolutely. And so let's do that. Let's talk about how all of this, the stadium example, the Shannon information versus specified information. Let's talk about how this applies to DNA.
Yep. So yeah, with the last few minutes that we have, let's pivot and let's look at what Stephen Meyer calls the DNA enigma. So essentially, the DNA molecule, its structure was first, you could say, elucidated. Its structure was first discovered in the early 1950s, around 1953. And one of the things that became very apparent very quickly, as I mentioned earlier, was that there's this double helix ladder that everyone's familiar with in the structure of DNA. And there's these bases, these base pairs that each side of the ladder is connected by these rungs on the ladder. And each side of the rung has a base pair on it that is essentially bonding, hydrogen bonding with each other. So that one of the things that became very apparent very early on to James Watson and Francis Crick was that there was no chemistry explanation for why the bases were bonding in the way that they were. Essentially, it was determined very early on that it looked random. Each of those rungs on the ladder, there was no reason for them to be paired up in the way that they were, chemically speaking. It just looked random. So it became, very apparent very quickly that even though it looked random for all the reasons we've been talking about, it was a problem of combinatorial inflation. It was very unlikely for it to happen that way. So, and even backing up a little bit more, in the early 1900s, it became very apparent that DNA had a very vital function to the self-replication of cells. So the fact that DNA had a structure that didn't have an explanation based on chemistry, but it was carrying a ton of specified information that was at the heart of what causes cells to be alive, what makes something differentiated between, a rock and an animal. It was all rooted in the chemical structure of DNA, but there wasn't a chemical explanation for why it was structured the way that it was in terms of the rungs on the ladder. So it was really in the 1960s that the what's now called the genetic code, and that has to do with how those rungs on a ladder are essentially function like computer code that then specify the production of proteins that allow a cell to work. So Meyer essentially coins this term, the DNA enigma. There may have been others before him that used it, but he likes to use the term the DNA enigma, enigma being like a mystery. So he essentially says, what is the DNA enigma? And sometimes you'll hear people talk about DNA and they'll say, well, the structure is super complex, or the fact that there's code there is the enigma. Really, none of these things are the ongoing mystery today. The fact that we know the structure, we know what DNA does, we know the code, and we know how it works. So what the DNA enigma is, the mystery, is how did the computer code get there in the first place? So just like all the other non-biochemistry examples that we're talking about, just like that is highly improbable specified information, it was realized by the 1960s that DNA contained a ton of highly specified information that acts just like computer code. and it's happening in every cell and every living thing on the planet. So the fact that you essentially have a computer program running in every one of your cells, we know how it works. We know what it does. We're learning a lot about it. Every decade, new things are being uncovered that are making us, more impressed with what's happening naturally. But the thing that is still a burning question, and the question is growing ever greater, is how in the world did it get there in the first place? And if you go back to your naturalistic worldview mindset, you're not going to allow intelligence into the room, so you have to explain it either by chance or necessity. So we're going to dive in and look a little bit more at specified information at the biomolecular level, because I really want to, I don't want to just, glance over it. I want to really explain exactly what we mean by genetic code. But before we jump into that a little more, Ruben, I don't know if you wanted to interject anything else in there, or if you wanted to, I think I had a couple of quotes in there. I don't know if those would be worth sharing as well.
Yeah, I can put them up. There you go. And so there's sort of just some quotes talking about how DNA is very similar to binary code. Binary is essentially, you only got two possibilities, 0 or 1. And so that's binary. And that's much of the way computers communicate. And so Bill Gates says human DNA is like a computer program, but far more advanced than anything we've ever created. And Richard Dawkins says the same thing. The machine code is uncannily computer-like. And he says that the pages of a molecular biology journal might be interchanged with those of a computer engineering journal, which I think is interesting. And so, yeah, what you said, I know people will say, well, the DNA is not really like a code. But that's what we see in the literature. And you get on PubMed and do any type of search on DNA, and you'll find that language code come up quite a bit. And Bill Gates, he's not a biologist, but he does understand computer programming, and he says DNA is like a code, and so does Richard Dawkins. And so, yeah.
Yep. So there we go. So moving forward, I wanted to really make the point that basically DNA and proteins, you can't have one without the other. It's essentially a chicken and the egg problem. That's something Meyer talks a lot about in Signature in the Cell. And I think it's something that needs to be really understood, is that when we talk about DNA and why is DNA so central to this origin of life argument, essentially, DNA is a chemical. It's one long biomolecule. Each one of your chromosomes contains one molecule of DNA that's all bunched up on itself. And it contains all of these instructions for what your cells are supposed to do and how they replicate and how they function. And the way that it does that is DNA contains the instructions for how to build proteins. So proteins are, and it does that via the genetic code. So proteins are these, basically a lot of times in literature, proteins will get referred to as the biomachinery of the cell. So it's the code in DNA that is telling proteins how to be made. So as you can see on the left side of the screen there, you've got your familiar double helix of the DNA. You see each of the rungs on the ladder has the different base pairs of the different bases. Yeah, there you can see a little better zoomed in. So G always bonds with C, T with A, and won't get into all the chemistry of that. But essentially, it is the sequence in which those bases are arranged that tell the transcription process, which is governed by RNA and other proteins, exactly how to make a protein. So what you do is but basically this is a language, right? So the genetic code is a language. So the language itself has 4 letters in it. So the 4 letters are A, T, G, and C, and that's the language in DNA. And kind of technical reasons, but in RNA, its language is A, U, G, and C. And so there's some kind of translation between 2 different languages that goes on there. And so this language has 4 letters, and every word in the language is 3 letters long. And so if you do the math, you got 4 times 4 times 4, you have 64 possible words that you can spell in this language. So you always take the first letter, and then the second letter, and then the third letter, and that makes a different combination. So like the very first one on the top left, if you have U, that combination will make phenylalanine. So that's abbreviated PHE. So if you go through and count, there's 64 possible combinations, and what each of those combinations of what's called triplet codons represent are one of 20 amino acids. So you get each of the 20 amino acids, and then you also have some stop codons and a start codon. And essentially, during the transcription process, when RNA is reading the DNA, it breaks open that double helix ladder, and it starts reading the sequence of code on the DNA backbone. essentially that start codon tells it this is where you need to start making a protein, and then it reads every 3 letters and it determines what amino acid should go, in the sequence according to that way. So it'll keep going until it gets to a stop codon. So if it gets to UAA on the mRNA molecule, then essentially it stops and it says, okay, that's my protein that I've built. And all down the backbone of DNA, it's coding for different proteins. And so that's what we mean by the genetic code. So going back to the example with the gibberish letters versus the non-gibberish letters that actually spell sentences, you can see the direct analogy here. So some of the sequences of the DNA bases make certain types of proteins, others make other types of proteins. But a point that you made earlier, Ruben, is if that basketball falls on the keyboard, there's a whole bunch of different ways it can make gibberish, but very few ways that it can make a cogent, coherent sentence. Right. And the what we see with proteins is there's a very small fraction of possible combinations of amino acids that actually make functional proteins. Such a small fraction that it's actually about 1 in 10 to the 74 possible combinations for 150 amino acid protein.
Yeah. So what you're saying is, first of all, proteins. We got to have proteins to live. That's how everything in the body works. That's what makes a certain cell a certain type of cell. And so in order for us to have a protein, it's like DNA is the instruction set. And so you go through all of these base pairs and all of these codons.
Exactly.
And
yes.
They push out amino acids, and these amino acids chain together as well to form proteins. So it's basically like building sentences. There's literally information in DNA that tells your body which proteins to make and which ones you need based on the cell and stuff.
Yes, exactly. And really the crazy thing about it is that DNA is a molecule and a protein is a molecule, but we cannot just sit down and make them in a lab. We can't just mix the right combination of chemicals together and get a protein, or just mix the right combination of chemicals together and get DNA. Even in a lab, we need some pieces of DNA to make proteins, and we need proteins to make DNA. And certainly at the cellular level, you can't get one without the other. So there's really and truly a chicken and the egg problem here in terms of DNA has all the information on how to build a cell and how to make a cell function, and proteins are the biomachinery that actually make that happen and make it work. So it just like the falling in a hole and needing a ladder to get out, it begs the question on, if you need one to make the other, how did that cycle get started in the first place? Like, who put the ladder in the hole to get you out of the hole? Essentially, we've kind of nailed down the chicken and the egg problem and talked about how that's important. And so in terms of talking about the specified information in a cell, the interesting thing is that DNA has all this information in its linear sequence, and it's the sequence in the DNA that determine the protein sequence, and it's the protein sequence that determine its structure, right? So on the slide, I have essentially showing there's different levels of structure within proteins. So you have the primary structure of a protein is that linear sequence that we're talking about in the upper left. So essentially, as you mentioned, Ruben, as you link those amino acids together, that is the primary structure of a protein, just its linear one-dimensional sequence. So in a cell, if it was just floating around like a spaghetti noodle, it really wouldn't do anything useful. It doesn't actually exist like that in a cell, because each of those amino acids are chemicals, and each of those chemicals have different sizes, and they each have different charges. Some of them are more positively charged, some of them are more negatively charged. So those different charges interact with each other, and those different sizes interact with each other. And it causes the protein locally to begin folding up on itself. It's called the secondary structure. There's two main different types of secondary structure. There's the alpha helixes, which is the little red kind of corkscrew looking thing. And then there's what's called the beta sheets. So essentially, it's the one-dimensional structure of the protein leads to these two-dimensional structures. And then if the sequence is right, then it begins to form what's called tertiary structure. And as you kind of zoom out on the molecule, it begins to fold up on itself more, and you get these neat arrangements in 3 dimensions of these different alpha helixes and beta sheets, and it forms essentially this glob, but a glob of a very specific 3-dimensional shape. And so that's the tertiary structure. And then finally, that sequence eventually is what will cause the quaternary structure. So because of its specific arrangement in 3 dimensions, when it folds up into this tertiary structure, you can have different monomers that all bond together and form, basically an aggregate of different proteins coming together. So in the example shown, there's 3 different monomers here. And so those are 3 different molecules that have all come together in 3-dimensional space to perform some function. So typically, proteins are going to be act as enzymes that are going to catalyze reactions, help reactions happen faster that otherwise wouldn't be able to happen. So keep in mind this kind of beautiful, elegant, highly specified 3-dimensional structure at a biomolecular level is happening because of the 1-dimensional sequence of the protein, and that 1-dimensional sequence of the protein is all because of the 1-dimensional sequence of the DNA. And so then if we move forward, this 3-dimensional structure is what ultimately gives a protein, as I mentioned, its enzymatic function. So this is actually a protein that I worked with in graduate school. There were a couple different proteins that we worked with in our lab, but this protein exists in a soil bacteria known as Pseudomonas aeruginosa. And on the left-hand side is the protein called azurin, and this is the azurin tetramer. So azurin is a relatively short protein, about 128 amino acids, and it binds to a copper atom. So the little blue dot on the left-hand side is a little atom of copper metal that is bound by this protein. And you can see the tetramer means that there's 4 different monomers bound together. You can see there's 4 different little blue dots there. So that's a tetramer that it's come together. And you can see its 3-dimensional shape with all the little amino acids hanging off into 3-dimensional space. Well, what gives it the ability to bind to this copper atom? Well, on the right-hand side, you can see a more zoomed-in view. And this is just a computer model, obviously, of what it looks like in 3-dimensional space. Well, what gives it the ability to bind to this copper atom is the arrangement of its amino acid residues in 3-dimensional space. So there's 5 different residues that are shown here. And you can see the little dashed yellow line. So on the right side, the copper atom shown in more of a gold color there, or I guess you could say a copper color. But it's bound in that location based on the charge and size and properties of the amino acids at those different locations on the protein. So the 1-dimensional sequence of the protein ultimately causes this 3-dimensional shape and charge and properties that allow the protein to bind selectively to this copper atom. And what this protein does is it allows it changes the redox state of that copper atom, and it'll change its charge. So by doing that, what it enables this bacteria to do is this bacteria is involved in the denitrification process in soil. So it's pretty amazing that the code in DNA, the sequence of these bases in DNA, ultimately are what cause the 3-dimensional structure in this protein to allow this bacteria in the soil to remove nitrogen or help the soil get rid of nitrogen in the soil. So it's like, to look at this and just say this happened by chance, that this could have come into existence by chance, is to completely ignore the amount of specified information that's here. Like, yeah, it's highly improbable that this protein sequence would have come together just by chance, but how much more improbable is it that, this is a whole nother level on top of the sentence versus the gibberish that we were looking at earlier. These are chemicals in 3-dimensional space that are existing the way that they are because of what's acting like a computer code in its DNA. So I thought this was an interesting example to show kind of linking from the 1-dimensional information to the 3-dimensional structure, and then show how the structure of the protein is what gives it its function. And it gets its function all because of the information that exists within DNA. I don't know if you have any additional thoughts on that, Ruben, or if my connection's still okay.
No, yeah, it's good. It's good. I wouldn't worry about it. But and so we see essentially what you're showing us is how much information DNA has with regards to proteins that are needed for whatever reason. So different proteins are needed for different things, and so they're made up of different amino acids so it will fold in a specific shape to do those specific things. And it's very much, I want to say, I don't want to undersell it. It's very much like how we put letters together to form words to make sentences, to make paragraphs, just to put it simply. This is way more complicated than that, but just to put it simply for people who don't know what all of this is, but it's very much like we put letters together to make words, and then we put those words together to make sentences, and then we put those sentences together to make paragraphs, and all of it has a meaning. And do we reasonably expect stuff like that to happen just by chance. Even given the given time, even given the time that all the time that the universe has, do we expect all of this to happen by chance? And you'll talk more about that with regards to DNA and the odds of that. But yes, just to put it simply, that's kind of what's going on here. DNA contains information to build very complex molecular machines. So
Yes. No, thanks for adding on to that, Ruben. Essentially, Ruben, you mentioned a few minutes ago about how proteins were involved in the production of proteins. Just wanted to mention this briefly. You were talking about the transcription process, which is how messenger RNA is copying information in DNA within the nucleus of a cell and sending it outside of the cell. So DNA always exists in the nucleus of a cell, and then through the process of translation, the information that's encoded on messenger RNA gets essentially turns into proteins outside of the cell, and it gets turned into proteins in a ribosome. So, the picture on the left is kind of what you typically see in like maybe a ninth grade or 12th grade biology textbook. And it would just show a very cartoonish version of how proteins get made. And the little pink dots that are linked together are showing a chain of amino acids getting linked together in the ribosome. They're getting brought to the ribosome by the transfer RNA. The messenger RNA is carrying the information from the DNA to the ribosome. And then, what's leaving is a fully formed protein. Based on what we've talked about and about the structure of proteins and how proteins fold, one of the things that blew my mind whenever I first learned it is that the ribosome is not a, squiggly little cartoon that's shown on the left-hand side of the drawing. The right-hand side is the ribosome of a bacteria that I just pulled off the internet, but it's a very simple form of one. And basically, a ribosome is made out of RNA and proteins. So the ribosome is the factory where proteins get made, and it itself is made out of proteins. So just kind of hammering home the point that you're talking about of, it goes back to the chicken and the egg as well. It's like, okay, the factory where proteins are getting made in every cell in your body is made in this thing called the ribosome that is essentially made out of proteins, made out of dozens of proteins. And they're all clumped together, and somehow they beautifully all work, and they do this billions of times per second, making new proteins. So it's pretty amazing. And it's pretty amazing that, there are many people who learn this and understand this much better than me. And they give not a second thought to the idea that, that this had to have been designed. They think, somehow it's possible that we can explain that this happened by chance. It's just really absurd on its face to me.
yeah, and so what some people will say is, okay, well, just give it enough time. Maybe the universe has enough quote unquote probabilistic resources. And that's what they mean whenever they say, give it enough time and this sort of thing can happen. And so let's talk about that. Let's talk about even, okay, how much time would it take, or does the universe even have enough time, right? The science sort of has a time that the universe has been in existence for. And so does the universe even have enough time to solve this problem via chance?
Really, that goes back to the stadium example we were talking about earlier. If you kind of held that number in your head, the number of possible ways of arranging 10,000 people in 10,000 seats, if you keep that number in that example in mind, do you have enough probabilistic resources to do certain things? Well, I think we mentioned the probabilistic resources of the universe are estimated to be around 10 to the 140th power. And that is, so 10 to the 139th power. What that number is that's essentially saying if I take every atom in the universe and I let each of those atoms interact as fast as they possibly can, according to quantum mechanics, have the fastest possible interaction rate that they can, and I let them do it for 14 billion years, then how many total interactions is that? How many total discrete events is that? And it works out to be about 10 to the 139th power. So that's the probabilistic resources of the universe. So when you have a problem that you want to attribute and say this happened by chance, but the probabilistic resources of the universe are greater than this number, then it happened with specificity, meaning that there was a high degree of specified information, it doesn't make sense that it would have happened by chance. So let's look at what was the probability that a cell could have formed by chance. So the first thing that we'd have to do is we'd say, okay, first we need to form a single functional amino acid. So what Meyer does in Signature in the Cell is he calculates that probability. So a relatively short protein has about 150 amino acids in it. And the probability of finding one protein of that length that has functional significance, meaning if you think back to its structure, if you sequence those amino acids together in a random way, typically it's not even going to fold up on itself. It'll just turn into basically a spaghetti noodle floating within a cell. It's not actually going to fold. It's not going to have any three-dimensional shape. So the odds of finding a single protein that has a functional structure is about 1 in 10 to the 74th power, which is incredible odds in and of itself. I mean, there's more than 10 to the 74th atoms in the entire universe, but it's not by much. I think the estimates are that there's only about 10 to the 80th power atoms in the entire universe. So saying that you're going to have 1 in 10 to the 74th is just absurd. So then on top of that, if you want to form a functional protein by chance, you also, when those amino acids come together, keep in mind these aren't just like Legos that you're sticking together. These are chemicals, and these chemicals can form other byproducts. They can undergo other reactions besides just linking together in a chain. And there's been a lot of experimental work done that's shown only about 50% of the molecules, the amino acid molecules, will actually form peptide bonds. About 50% of the time they'll form other bonds. So that math works out to about 1 in 10 to the 45th possibility that you're only going to form peptide bonds in that chain. And then lastly, kind of the other thing that is really killing the chance hypothesis is that you have 20 different amino acids in every protein in a cell, but those amino acids can exist in 2 different forms, and they're called left-handed amino acids. Essentially, it gets to the fact that those amino acids can have mirror images of each other, just like I have a left hand and a right hand. They're essentially the same, but they're mirror images of each other. It's the same with these molecules. So, but only functioning proteins and living cells, they only have left-handed amino acids in them. So you take these 3 probabilities into account, and there's about a 1 in 10 to the 164th power of forming one single functional amino acid that's about 150 amino acids long. So it's incredibly low odds that one functional protein would form by chance. But the problem with trying to get a self-replicating cell, as you mentioned earlier, you need a lot more than just one functioning protein. Proteins do a lot of different things. So to just get to the point, you need, conservative estimates are that you need a minimum of about 250 functioning proteins within the simplest living cells. So if you take 1 in 10 to the 164th odds times 250 different proteins, you come up with a number that's roughly around 1 in 10 to the 41,000th power. That's the odds of a minimally complex cell forming by chance. So it's incredibly low odds. The universe isn't nearly a big enough place for this to happen by chance, right? We've already taken into account the probabilistic resources of the universe, 10 to the 139th power. So essentially, mathematically, you can show that something that is this improbable to happen by chance, 1 in 10 to the 40-something power odds, and it also carries layer upon layer of specified information within it. There is no scientific or logical reason to believe or assume that chance has any probability or any chance of making this happen, right? So this already takes into account if you have an old universe. This already takes into account if you have a really big universe. And there is no way that the chance hypothesis caused life as we know it to form by chance. So that's essentially one of the key arguments that Meyer makes in Signature in the Cell. And I think it's an extremely powerful case to make for, building our faith in intelligent design and in a creator, and understanding that if it didn't happen by chance and it didn't happen by some law-like necessity, intelligence is the only other way that we know of that effects can happen, that things can happen.
Right, exactly right. And so I'm going to briefly summarize this. And so Douglas Axe, was it Douglas Axe or William Dembski that came up with 1 in 10 to the 74th of a minimally functional protein?
Yeah, it was Doug Axe. There are a lot of other people that did research on it. Okay. Yeah, Doug Axe is 1 in 10 to the 74th.
So Douglas Axe came up with this probability of 1 in 10 to the 74th power. Those are the odds of finding a single functional protein. But the thing is, you need to have a protein with peptide bonds only when talking about amino acids anyway, with peptide bonds only when talking about a protein. And also you need left-handed amino acids, and left-handed and right-handed amino acids occur at the same rate in nature, right? Isn't that right?
Yes, in nature they do, but in functioning proteins, you need only left-handed amino acids to form a functioning protein.
Right. So if you're just going to form this protein, from essentially nothing. You've got to overcome all of these odds. Okay, so you first of all 1 in 10 to the 74th power of just forming a functional protein from amino acids just laying out there, and then it's got to be peptide bonds only, and then it's got to be left-handed amino acids only, and the odds of all of that coming together is 1 in 10 to the 164th power, and then you need 250 of those. And so you got to multiply by 250, and you're left with 1 in 10 to the 41,000th power. That's a huge odd. And the probabilistic resources, even if every atom in the universe had, the entire amount of time that the universe has been in existence, billions, 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 billions of years, you only have 10 to the 139th number of guesses. Let me just put it simply. Number of tries. And so that 10 to the 139th just cannot match 1 in 10 to the 41,000th, right? And so essentially chance has no chance here. Typically where you want to start using the chance hypothesis is if you can cover more than half, right? But here you can't even cover more than half. And so you are less than likely of this. It's less than likely, way less than likely, that the odds of forming a minimally complex cell of that happening by chance. It's just not going to happen. There's not enough resources in the universe. And so, like you said, the only thing left is a designer and intelligence. What do we know from our repeated experience? Where does information come from? And I'm talking about specified information with meaning. Through our repeated experience, we know that it always comes from an intelligence. And so, just to put that aside and say, chance just doesn't work based off of these odds. So exactly right. Anything else? I'm going to turn it back over to you.
Okay. No, great summary, and couldn't agree more. And yeah, I would say too, I think we both use the phrase there, life as we know it. And, sometimes that gets used and that'll kind of segue into our kind of final part. But sometimes people will say, well, life as we know it couldn't have formed this way. And, in pop culture, maybe in, the classroom, a lot of times people will still lean on this chance hypothesis. But if you start getting down to it, I think all scientists would agree that essentially that this probability holds that you can't just have a cell. The simplest cell as we know it can't just form by chance because of these odds. So that this isn't something revolutionary here that scientists don't understand. But I think in pop culture, and in our media and our movies, a lot of times that they want the general public to not understand that, or to still be kind of duped into thinking that this can happen by chance. And I would say really up until about the 1980s, people were trying to come up with how could the simplest cell as we know it form by chance. And they were failing. And because of the probabilities that we're showing here, it was, pretty widely accepted by the mid 1980s that it couldn't happen by chance. So and I think the best way to show that is that enter in the mid 1980s the RNA world theory. So we won't go into the details on this. Meyer covers it. I think it's in chapter 14 of his book. But the RNA world theory, I think, is the fact that Origin of Life scientists developed a theory that is based on the fact that they basically have a theory that before life as we know it, all life was RNA-based world. Instead of DNA-based life, it was all RNA-based life. And they try to use this to circumvent this chance problem, this probability problem. So I think the fact that they even came up with this theory is, really a tacit admission that the chance hypothesis doesn't work. They had to come up with a theory to explain why their chance theories don't work. And interestingly, about 10 to 15 years ago, in the literature, you start seeing more mentions of the need for a pre-RNA world theory. And, Meyer mentions 5 different major problems in his book on the RNA world theory. And one of the biggest ones is that RNA presupposes the existence of biological information, and it still doesn't explain the source of the information. And so now kind of the leading theory on how life could have originated by chance is this theory that, there was an RNA world before life as we know it, and then before that, some sort of pre-RNA world. And it really, I started by reading some quotes from Richard Dawkins talking about believing in spite of the evidence. Sometimes you'll hear people talk about a blind faith. In my opinion, it really gets to a point where you start to have a blind faith in in natural causes. You start to see something where the evidence in nature points so strongly to a designer, to a creator, that you start to just have this blind faith that there must be a natural explanation. And you start, and even when the evidence doesn't suggest it, then you have to come up with theories that presuppose the evidence and really contradict what you're seeing evidence-wise. So I think at another time we'll definitely maybe dive into these more, the RNA world and pre-RNA world. I just wanted to mention them because I know prior to about 60 years ago, what we've been talking about with the chance hypothesis, that was really the leading scientific consensus for how life could have started naturally. And it's really not today. So anyone who's watching that maybe wants to run off and try to find a reason, an alternative explanation, RNA, we haven't really talked about it, but the RNA world and pre-RNA world theories are, more current theories on how this could have happened. But it's the same problem. Once you get down into it, they're still relying on chance. They're still presupposing information, and it's still a problem of extremely unlikely probabilities and tons of specified information that you're trying to explain by chance. And we just know that you can't do that. Meyer, he essentially talks about an inference to the best explanation as the way that he uses it. And we've kind of hit this a lot already, but I challenge anyone to come up with another cause besides necessity, chance, or intelligence for any event that you see in everyday life. And if chance can't do it, and there is no law-like necessity explanation for how living cells came into being, then intelligent minds are an intelligent mind is the only logical cause that makes really any sense. So anyway, these are really it's a lot of information to try to cram into a short amount of time. But it's this train of evidence, this logical train of evidence, is really what has over the last decade or so strengthened my faith. If I have questions about anything, or maybe in times if I have doubts, this is one really pillar that I can go back to and know that I'm not here by accident. I don't care how many militant atheists tell me that I'm here by accident or that I'm here by chance. I know that just does not make sense. And I think this is a topic that more people can lean on to really strengthen their faith as well. I appreciate you talking to me about this afternoon, Ruben.
Yeah, absolutely. Absolutely. I'm sure that it is beneficial for the people who have watched. Let's close out with a word of prayer, and then we'll be done with the study. Almighty God, we come before your throne, thanking you for this time that we've had, Father. We thank you for DJ and the excellent studies that he's done, and just his background, and the fact that he's been able to dig deep into these topics and strengthen his faith and strengthen our faith as well. Father, we pray that you'll be with us and help us not to be afraid of questions. Help us to not be afraid to have questions or ask questions, as long as we ask them with an honest heart, seeking the truth. Again, Father, we pray that this study has been a benefit to us and to those who have listened, that has been able to strengthen our faith. And we pray that ultimately through this, we will better be able to bring glory to you and teach others. Pray this in Jesus' name. Amen.